In the beginning, there was no ticking clock, no sun to rise and set, no sense of before or after. Time, as we know it, was not yet born. Then, in a moment of unimaginable force and brilliance, the universe erupted into being, space unfolded, matter scattered. And with it, the strange and elusive current we call time began to flow. But from its very first breath, time has never been as simple as it seems. We tend to think of time as a reliable companion, always moving forward, never stopping. Seconds pass, minutes accumulate, and the hours stretch into days. It's in the turning of the seasons, the rhythm of our breath, and the growth of our children. We measure our lives by it, schedule our hopes around it. And yet, this companion we trust so deeply is anything but constant. Imagine a journey won not across countries or oceans, but across the very fabric of reality. You and your closest friend, once side by side, board separate spacecraft. Their ship accelerates, inching ever closer to the speed of light. You remain behind, watching the stars shimmer and stretch. From your vantage point, time begins to betray its uniform mask. Your friend's ship, once brisk and steady, now creeps forward as if wading through honey. Movements stretch like shadows at sunset. Voices drawl into distorted echoes. Minutes for them become hours for you. But inside the ship, your friend feels nothing unusual. Time remains their faithful ally, unwavering and steady. They sip tea, laugh at old jokes, watch the cosmos stream past, all unaware that from your eyes, they are drifting into the slow ballet of time's dilation. This is no illusion. It's the heart of reality, unveiled by Albert Einstein over a century ago. Newton, centuries before, had imagined time as an absolute river, flowing evenly through all corners of the universe. But Einstein saw something deeper, more mysterious. He realized that time was woven into the very tapestry of space, and like fabric, it could stretch and twist, motion and gravity. He discovered were the hands that shaped it. Near massive objects, like black holes, gravity pulls at time itself. Stand close to one, and seconds extend like taffy. Move faster and faster, and time starts to yield, folding in on itself. This is why GPS satellites, orbiting high above Earth, tick slightly faster than our clocks on the ground. It's why astronauts return home a little younger than if they had stayed. These are not tricks. They are glimpses into the hidden nature of time. To truly understand this, we must journey backward back to the beginning. In the newborn universe, all matter and energy were crushed together into a searing, dense cradle. Gravity reigned supreme. In such a place, time crawled. The equations of relativity tell us this plainly. The stronger the gravitational field, the slower time flows. Imagine the first moments after the Big Bang as a frozen tableau, where the universe, still infant and fiery, pulsed in slow motion. Each second was thick with resistance. This warping of time, known as gravitational time dilation, is not confined to the past. It lingers. It governs the flow of time on planetary surfaces and in orbit, in collapsing stars and in the vast vacuum between galaxies. Time is not a universal tempo, but a local rhythm, changing with every step you take. And yet, motion plays its own game. Special relativity shows us that speed, too, slows time. A traveler moving near the speed of light will experience mere hours while centuries pass for those left behind. The twin paradox, a thought experiment turned physical law, illustrates this. One twin remains on Earth, living a normal life. The other soars through space at incredible speeds. When they reunite, one has aged, the other has not. This is not magic. It is the universe obeying its own rules. All of this challenges our senses, our instincts. We want time to be fair, equal, shared, but it isn't. It's shaped by where you are and how fast you're going. It is sensitive, reactive, alive in ways we never imagined. When we gaze at galaxies billions of light years away, we are not just seeing distance, we are seeing old light, stretched and slowed by the journey. Those ancient stars blink at us through the haze of history, their rhythms slowed by time itself. We measure this phenomenon as redshift, the elongation of light waves as they travel through expanding space. But behind this shift is a deeper truth. Time itself was different back then. Quasars, the brilliant hearts of early galaxies, flicker more slowly than their modern cousins, not because they were slower, but because the very universe was dragging time through the mud of expansion. To picture this, imagine a steep valley. At the bottom, near the black hole or the Big Bang, time flows like a sluggish stream. As you climb the slopes, away from gravity's grip or speed's embrace, the stream quickens. This graph of time versus position would not be a straight line, but a curve dipping and lifting, shaped by the contours of space-time. And this brings us to an even stranger frontier time travel. Not just forward, which we already accomplish in small ways, but backward. Here, paradoxes bloom. The grandfather paradox asks, what if you went back and prevented your own birth? The bootstrap paradox imagines a book handed back in time to its own author. Who wrote it? Where did it begin? These are not just riddles, they are tests of our understanding. They expose the fragility of our logic when time loops upon itself. Some theorists propose alternate timelines, parallel universes born from each divergence. Others say the universe would protect itself, never allowing such contradictions to form. And perhaps they're right. But even if time travel remains fantasy, the way time bends and bows is not. It is real, measurable, and deeply unsettling. It tells us that our lives are not ticking along some grand, cosmic metronome. We are each riding our own current, shaped by the hills and valleys of the cosmos. So next time you glance at the clock, consider this: its ticking is not universal. It is a local dialect of time, whispered to you by your place in the universe, in the grand, ever-unfolding story of reality. Time is not a line, it is a living, breathing thing, and we are all suspended in its flow, drifting not together, but apart, each on our own stream, carried by gravity, speed, and the great unfolding mystery of the cosmos. The ancient universe whispered secrets long before language gave them names. In its silence, patterns formed spirals, waves, collisions that echoed across the expanding void. And in that quiet, time continued to ripple outward, touched by forces more powerful than imagination. But the deeper we peer into the cosmos, the more we realize understanding time is not about clocks or calendars. It's about perception, and how the universe stitches past, present, and future into a single, ever-shifting tapestry. Let's descend now into a realm where time is not just a feature of the cosmos, but a lens through which reality itself takes shape. Consider consciousness the spark that lets us mark the passage of time. Without awareness, time becomes meaningless. A rock does not feel the dawn. A wave does not mourn the tide. Only minds like ours give time its rhythm. But what if our very perception of time is flawed? A mirage crafted by biology and bounded by memory. Neuroscientists have long marveled at how our brains carve time into segments. Moments feel longer or shorter based not on duration, but on emotion. A joyful hour with a friend feels fleeting. A minute in fear stretches to eternity. This elasticity is no accident. It is our brain's way of prioritizing experience. But what if the universe, too, experiences a kind of memory, a record of past states etched into its structure. Every particle's position, every echo of a photon, tells a story. The cosmos, in a sense, remembers. In physics, this concept appears as entropy, the tendency for systems to move from order to disorder. Entropy is why a shattered glass won't reassemble itself, why smoke doesn't return to a fire, why time has a direction. This direction, known as the arrow of time, flows inexorably forward, from low entropy to high. And yet, the laws of physics are time-symmetric. If you reverse the equations, they still make sense. So, why does reality insist on marching forward? The answer may lie in the Big Bang. At that first moment, the universe began in a state of incredibly low entropy, an almost impossibly smooth arrangement of energy and matter. From that cosmic seed, disorder bloomed, galaxies formed, stars ignited, and planets spun into existence. In this view, the arrow of time exists not because time itself is biased, but because the universe started with such astonishing order. Imagine a deck of cards perfectly arranged. The moment you shuffle, disorder increases. Each shuffle creates more possible outcomes, more randomness. That's entropy. And just like with the deck, the early universe was exquisitely ordered. Everything since has been a shuffle, and every shuffle drives the arrow of time. But entropy doesn't just explain why time moves forward. It hints at a cosmic memory embedded in matter. The universe isn't just expanding, it's recording. Each new arrangement of particles, each shift in energy, is a page in the story of existence. The past doesn't vanish, it becomes part of the structure of everything that follows. Perhaps that's why the past feels fixed, while the future remains fluid. Now, let us shift from the grand to the granular. Picture a single atom on a distant planet, caught in the orbit of a star we'll never see. Its electrons vibrate. Their probabilities spread across time and space. In quantum mechanics, these vibrations are governed by a mysterious interplay of chance and causality. At this scale, time is not smooth, it's jittery, probabilistic, as if stitched together from quantum fragments. Physicists describe this with the term quantum decoherence. As quantum systems interact with the environment, they lose their indeterminacy and settle into definite states. It's this process that allows the classical world, the one we experience, to emerge from the quantum fog. Time, in this sense, is a byproduct of decoherence. When particles lock into history, the flow of time becomes real. Without decoherence, there is no clear past or future, only a blur of possibilities. This raises profound questions. If decoherence gives birth to time, then time itself may not be fundamental. It may be emergent, something that arises when complexity reaches a certain threshold. In a world of pure quantum states, past and future are illusions. Only the wave function, the full description of all possible realities, exists. And yet, here we are, living, breathing, counting the seconds. So what is the bridge between quantum timelessness and our lived experience? Some theorists propose a model known as the block universe. In this view, past, present, and future all coexist in a four-dimensional structure. Time doesn't flow. It simply is. Each moment is a coordinate in space-time, fixed and eternal. We, like characters in a novel, experience the story page by page, though the entire book already exists. The block universe challenges everything we think we know about free will. If the future already exists, are we truly choosing our paths or merely uncovering them? It's an unsettling idea, one that reframes time as a landscape rather than a river. But perhaps unsettling ideas are necessary when trying to grasp something as elusive as time. Others counter with a model of the growing block universe. In this version, the past and present are real. but the future is not yet. Time grows like a tree, each moment adding to a trunk of cosmic history. This view preserves a sense of becoming, of unfolding, of potential. It aligns more closely with our intuition that the future is open, unwritten. Still others explore loop quantum gravity, a theoretical framework that suggests space-time itself is quantized, made of tiny loops woven into a spin network. If true, then time might be composed of discrete units, like frames in a film reel. Continuity would be an illusion, just as a movie appears smooth even though it's made of still images. This theory would mean that between each tick of the clock, there exists a gap, an invisible breath where nothing happens, yet everything prepares to happen. We are left with a mosaic of possibilities: time as memory, time as entropy, time as quantum emergence, time as a static block, time as a growing organism, time as a flickering illusion of discrete frames. Each model brings us closer to an understanding, but none fully captures the experience of being alive in time. And perhaps that's the point. Time is not just a dimension, it is the stage upon which meaning is born. Our memories give weight to the past. Our dreams infuse the future with significance. Our choices stitch the present with purpose. The more we learn about time's mechanics, the more we are drawn to its poetry. Because in the end, to understand time is to understand ourselves, not just as creatures who endure it, but as beings who shape it through thought, memory, and imagination. Time may be bent by gravity, slowed by speed, blurred by quantum uncertainty. But in every heartbeat, every tear, every laugh, we feel its passage, and that, more than any equation, is the deepest truth we know. The journey continues. In a universe where time stretches and curls like an ancient river winding through alien terrain, our attempts to understand it are like casting stones into water and watching the ripples collide. With each discovery, the surface shimmers anew, revealing depths we hadn't imagined. Now, we turn our gaze to the most enigmatic arenas where time behaves not only strangely, but perhaps incomprehensibly: black holes, cosmic strings, and the potential end of time itself. Black holes are not merely objects of immense gravity. They are gateways to extremes where space folds, light hesitates, and time itself grinds nearly to a halt. As you approach the event horizon, the boundary beyond which nothing escapes, the flow of time, slows to an imperceptible crawl. To an outside observer, an infalling object appears to freeze, forever suspended on the edge. Yet for the traveler, time remains normal until the final moment, a quiet descent into the unknown. This duality, where time appears frozen and flowing simultaneously, tears at the fabric of our understanding. Inside the event horizon, our equations break down. Space and time trade roles. The singularity, a point of infinite density, is not just a place but a moment in time where all paths end. What lies beyond is beyond our physics, perhaps beyond reason. But black holes may also be keys, not just tombs. Some theorists propose they harbor bridges, wormholes to distant parts of space and time. If such structures exist, they could allow shortcuts through the cosmos or even time travel, provided you survive the tidal forces. This is not science fiction. These solutions arise naturally in Einstein's equations. The question is not whether they can exist, but whether reality permits them. Parallel to this mystery are the threads of cosmic strings, hypothetical defects in spacetime that may have formed moments after the Big Bang. Infinitely long, yet unimaginably thin, they carry immense tension, warping spacetime in strange and beautiful ways. If two strings pass each other at high speed, they might create closed, time-like curves, loops in time. In theory, such loops could allow travel into the past. Yet nature, as it often does, may conspire against such ambitions. The chronology protection conjecture, proposed by Stephen Hawking, suggests the universe prohibits time paradoxes by making such loops unstable. A kind of cosmic firewall might ignite whenever we try to twist time into a circle. Time, it seems, resists being rewritten. As we ponder the far reaches of time, we must also consider its fate. What becomes of time as the universe ages? Cosmologists speak of several endings: the Big Freeze, the Big Rip, the Big Crunch. Each paints a different future. Each reshapes time itself. In the Big Freeze, the universe expands forever, growing colder and emptier until no heat, no light, no activity remains. Time does not stop. It becomes irrelevant. With nothing changing, no events occurring, time loses its meaning. It's a death not of destruction, but of silence. In the Big Rip, the fabric of space expands faster and faster, eventually tearing apart galaxies, stars, planets, atoms. Even time itself may fragment. As distances stretch beyond limit, causality shatters, and the arrow of time dissolves into chaos. The Big Crunch imagines a universe reversing course, collapsing inward until all matter returns to a singular point. Time, running forward all the while, may halt or even reverse in this final contraction. Could we experience our lives in reverse, unraveling memory by memory, breath by breath? There is also the possibility that time is cyclical. Some cosmological models propose a rebirth, a new Big Bang, following the collapse. Time, like a phoenix, rises from its ashes. In such a looped cosmos, history might repeat. Are we living a life lived countless times before? Each scenario forces us to ask, does time have an end? And if so, what lies beyond it? If time is a property of our universe, then its end might be the end of everything we can possibly know. Or perhaps, beyond the final tick, lies something stranger, another realm where time, if it exists at all, wears a different face. Still, time's story is not all distant speculation. It plays out intimately in our daily lives. Every human culture has invented ways to market sundials, hourglasses, atomic clocks. We build calendars, celebrate anniversaries, grieve the passing of years. Our lives are narratives written in the ink of time. Even our bodies are timekeepers, the ticking of the heart, the cycling of cells, the arc of aging, all bound to time's flow. But we are more than passengers. We are architects of memory and anticipation, bending time within our minds. Through stories, we travel to the past. Through imagination, we visit futures that may never come. We give time color, meaning, emotion. Art, music, and literature stretch time, folding moments into eternity. A song can make 3 minutes feel infinite. A photograph freezes a heartbeat forever. Through expression, we resist time's erosion. We tell stories not to stop time, but to live alongside it, to make peace with its passing. And yet, even peace is not always easy. Time brings change, loss, endings, but it also brings healing, growth, renewal. The same current that erodes also nourishes. We build dreams on its flow. So as we journey further into the nature of time, we find not just science, but humanity. Not just equations, but experiences. Time is not merely a dimension of the universe, it is the theater in which our lives unfold. To understand it is to deepen our place within it. Now, let us wade deeper into the mystery, not through galaxies or quantum loops, but into the nature of time as it relates to identity, memory, and the boundless ocean of imagination. If the universe writes its story in the motion of stars, we write ours through the quiet flickers of thought. And in that inner cosmos, time flows differently. The human mind is a time machine, not made of gears or circuits, but of neurons and stories. We travel backward in memory, sometimes so vividly that the past feels present. We leap forward in imagination, projecting ourselves into futures we hope or fear. This temporal elasticity is not just poetic, it's a neurological truth. The brain does not merely record time, it reshapes it. Studies have shown that when we recall an event, the same areas of the brain that were active during the event reactivate. Memory is not playback, it is reliving. This means the past is not gone. It's reanimated each time we remember. In this way, time within us is cyclical, not linear. A grief from 10 years ago can bloom with fresh tears. A joy from childhood can return with aching clarity. Our inner timeline is a spiral. And yet, memory is fallible. It blends, distorts, invents. We often remember what we wish were true, or what we feared most. The brain edits without our permission, inserting emotional truths where factual ones falter. This is not a flaw, it's a feature. Our memories shape our sense of self. They are less about accuracy and more about meaning. In this light, time becomes not a ruler but a brush, each memory a stroke of identity, painting who we are. And because memory is mutable, so are we. We are not static beings traveling through time. We are fluid, formed anew each moment by the stories we choose to remember. But memory alone doesn't define our temporal experience. Consider anticipation, the emotional resonance of what has not yet occurred. Hope, dread, wonder. These are not tied to the now, but to what might be. Our minds reach forward just as often as they reach back. Time's power over us lies in this dual tension, remembrance and expectation. Religions and philosophies have long grappled with this. In many traditions, time is a path to transcendence. Eastern philosophies speak of cycles, samsara, rebirth, karma as endless loops where time is not escaped, but mastered, enlightenment. In some sense, is freedom from the illusion of time. In the West, time often flows toward a divine culmination, an end, a judgment, a resurrection. Both views imbue time with spiritual gravity. But not all visions of time are hopeful. Existentialists like Heidegger frame time as the shadow beneath meaning. To live authentically, he argued, is to confront the reality of our own finite time. Death gives urgency to choice and weight to freedom. Without time, we would have no stakes, no reason to act. In this view, every moment is sacred because it cannot be reclaimed. The Latin phrase memento mori, remember that you must die, is not a morbid warning, but a call to awaken. To be conscious of time is to honor it. Art captures this reverence. A film is a measured dance through time, each frame a decision, each cut a shift in tempo. Great directors bend time, stretching it in a lingering glance, collapsing it in a montage. They show us that time is not just experienced, but orchestrated. Poets, too, are time sculptors. A single line can contain centuries. A haiku can suspend a second in eternity. Through metaphor, rhythm, and silence, poetry makes time feel, not just pass. Even architecture plays with time. Ancient temples, eroded by wind and rain, remind us of how long a stone can remember. A crumbling facade tells of civilizations past. We walk through cities like layered texts, reading the stories etched in their walls. But what of the time we cannot feel the deep time of geology and cosmology, the span of billions of years over which mountains rise and erode? Stars form and collapse, species emerge and vanish. This time is humbling. It reminds us that our lifetimes are flickers, brief and bright. And yet, even these flickers leave traces. A child's laughter, a carved name, a whispered idea all ripple forward. In physics, these ripples may echo as gravitational waves, tiny distortions in space-time caused by massive events. But in human terms, they echo in culture, memory, legacy. Perhaps that is the true triumph of consciousness, to leave imprints in time. So, we dance in this tension between insignificance and importance, between knowing we are small and choosing to matter anyway. We measure time not just in seconds, but in stories, not just in change, but in meaning. And meaning, unlike time, can expand endlessly. The clock ticks, the stars wheel, and within each of us, a universe of time pulses quietly. Let us now come to the threshold where understanding turns into awe, where the pursuit of time's nature begins to reveal something even greater connection. For in all our attempts to dissect time, to measure and model it, what we are truly seeking is our place within it. Time is not merely a backdrop to our lives, it is the thread that stitches us to one another, to the past, to all that might come. We live in time, but we also live through each other. Every conversation, every kindness, every shared silence is an exchange of temporal essence. When you remember a loved one, you do not simply revisit an image you cross time, reach backward and bring them forward into now. In this way, memory becomes a form of communion, and storytelling becomes a time machine that binds people across generations. A child's lullaby may contain echoes of a song sung 1,000 years ago. A sacred text, passed hand to hand, can carry the breath of the ancients through language. We defy oblivion. But even more than memory, empathy is the miracle that bends time. To feel another's sorrow as if it were your own, to inhabit their moment that is a collapse of separation. It is time folded not by physics, but by compassion. And perhaps, this ability to connect is humanity's most powerful defiance of entropy. We build cathedrals, libraries, cities not merely to endure, but to declare we were here, and we mattered. Our monuments may crumble, but the act of building is a statement against the erasure time brings, and though many voices are lost, each one carried forward changes the shape of the future. Consider the legacy of ideas. A thought, once spoken, once written, can ripple far beyond its moment. Newton's laws, Einstein's equations, a poet's verse, a scientist's vision, these do not remain locked in their own era. They radiate. They change the trajectories of lives yet unborn. The present, then, is never just a moment. It is an intersection, a collision of what has been and what could be. And at that intersection stands each of us, finite, yes, but capable of infinite resonance. When we speak of time, we are also speaking of loss. We lose people, places, eras, but we also gain. We inherit. We become. Time's passing is what makes beauty poignant and love enduring. The fragility of each moment is what makes it shine. Like a snowflake melting on a fingertip, its value is in its transience. This is the paradox we must hold. Time both takes and gives. It carves lines on our faces and wisdom into our hearts. It dissolves illusions, but reveals truths. It humbles us, but also empowers us to leave marks that outlast our days. So perhaps the true nature of time is not merely to measure, but to transform. To live in time is to evolve, to create, to heal, to remember, to hope. Time, then is not the enemy. It is the canvas, and what we paint upon it, our acts of love, of courage, of imagination, those become the constellations by which others navigate. We began this journey at the birth of the universe, among the rippling fires of creation. We traveled through stars and theories, equations and paradoxes. We stood at the edge of black holes, walked the quantum foam, and traced the arc of aging across the soul. We have glimpsed how time bends, stretches, loops, and sings. But in the end, time's greatest mystery may be its invitation, not to solve it, but to live deeply within it. To notice the light in a stranger's eye, to savor the echo of laughter, to forgive and be changed, to love, and let that love ripple endlessly forward. Because while time moves on, meaning does not decay. Every true act resonates beyond its hour. So, as the seconds gather and the stars continue their silent dance, let us not ask what time is, but what we will do with the time we are given. The journey through time is the journey through ourselves. And though the river flows forward, our footprints, our voices, our dreams, these remain endlessly.
Have you ever wondered what time truly is? Is it an invisible river sweeping us through the shores of memory and hope, or merely a mirage our minds conjure to make sense of the universe's chaos? Picture this. You're standing atop a mountain, gazing down at a valley stretching endlessly before you, where sunlight dances on leaves, and for a fleeting moment, time seems to hold its breath. But what if you were racing at the speed of light, or spiraling into the grip of a black hole? Would that moment still mean the same? Welcome to a journey into the nature of time, a concept as familiar as the beating of your heart, yet as enigmatic as the stars glimmering beyond the horizon. In the realm of physics, time is more than a sequence of ticking seconds. It's a dimension, the fourth dimension, woven intricately with length, width, and height to form the fabric of the cosmos we call space-time. Albert Einstein, with a mind that soared beyond his era, revealed that space-time isn't a static stage where planets and stars play out their cosmic drama. It bends, it ripples, and most astonishingly, it shifts depending on who's watching. Imagine an astronaut hurtling through space at near light speed. For them, time slows to a crawl compared to someone rooted on Earth. When they return, their clock might show mere years have passed, while those left behind have aged decades. This isn't science fiction. It's the breathtaking reality of time dilation, born from the elegance of relativity. Yet time isn't just numbers on a dial or equations on a page. It challenges how we perceive the world, beckoning us to dream of voyages across epochs. Could we wind the clock back to mend our mistakes, or leap forward to touch days yet unborn? As physicists probe time's essence, they find it's neither fixed nor absolute. In every reference frame, with every velocity or gravitational pull, time tells a different tale. This fluidity transforms it from a dry abstraction into a gateway to infinite possibilities. A twin on a spaceship ages slower than their sibling on Earth. A clock near a black hole ticks at a languid pace compared to one far away. These aren't quirks, they're windows into a universe where time dances to the rhythm of motion and mass. So join me as we step through that gateway, where science and imagination intertwine. We'll unravel not just what time is, but how it shapes the very fabric of our existence. From the ticking of a second to the stretching of eons, time is both our companion and our mystery, a thread tying us to the stars, yet slipping through our fingers like sand. Let's chase it together through the wonders of space-time and see where its currents take us. Delving into quantum mechanics, a new perspective on time. In the heart of modern physics, where the tangible dissolves into the probabilistic, quantum mechanics emerges as a governing principle of the very small. It is a theory that does not merely modify our understanding of reality, it revolutionizes it. Time, once an immutable backdrop against which all events unfold, begins to lose its classical coherence when examined through the lens of quantum theory. The certainty of past, present, and future, so deeply embedded in human intuition, yields to a reality where these distinctions blur, where particles transcend singular states, and where cause and effect entangle in ways that defy conventional logic. At the core of this quantum enigma lies the principle of superposition, the idea that a quantum system does not simply occupy a single state, but rather exists in multiple states at once. Schrödinger's famous thought experiment, in which a cat is both alive and dead until observed, serves as a metaphor for this strange duality. In a classical world, time is a linear progression moving forward in a well-defined sequence. But within a superposed system, events exist simultaneously, seemingly independent of a singular temporal flow. The distinction between before and after dissolves, leaving us with an unsettling question: is time truly fundamental, or is it an emergent property of a deeper, hidden reality? Even more profound is the phenomenon of quantum entanglement, in which two particles, no matter how far apart, remain inextricably linked. A change in the state of one instantaneously affects the other, a connection that appears to transcend the classical constraints of space and time. This eerie simultaneity suggests a universe where time may not be the independent parameter we perceive it to be, but rather a construct emerging from a deeper order, one where separations in time are as illusory as separations in space. If quantum mechanics is correct, and all experimental evidence suggests it is, then our conventional understanding of time may need to be reconsidered. Could it be that time, much like temperature or pressure, is not a fundamental aspect of reality, but an emergent property of deeper quantum processes? Could the apparent flow of time arise from the entanglement of information rather than being an intrinsic feature of the universe? These questions are not merely philosophical musings. They touch upon the very foundation of physics, from the birth of the cosmos to the structure of consciousness itself. As we venture deeper into the quantum realm, we stand on the precipice of a paradigm shift. The rigid, mechanical universe envisioned by Newton and even the relativistic space-time of Einstein may give way to a reality governed by probabilities, correlations, and an intricate web of quantum information. To understand time, we must first embrace the unsettling notion that it may not exist in the way we have always believed. Instead, time may be a thread woven from the very fabric of quantum interactions, an emergent symphony arising from a deeper, as yet unseen harmony of the universe. Quantum time travel, possibilities and paradoxes. Time travel has long been the realm of science fiction, a tantalizing fantasy where past and future become accessible like pages in an open book. Yet, as our understanding of quantum mechanics deepens, what was once mere speculation is now creeping into the domain of theoretical possibility. Could the fundamental principles of quantum physics provide a pathway to traverse time, allowing us to rewrite history or glimpse the unwritten future? If time travel is possible, even in the quantum sense, then the very nature of causality, reality, and human existence must be reconsidered. One of the most promising avenues for time travel emerges from the peculiar realm of quantum entanglement and retrocausality, phenomena that challenge our classical intuition about the unidirectional flow of time. In entangled systems, two particles, no matter how distant, share an instantaneous connection. This has led some physicists to speculate whether information might be transmitted backward in time, creating a bridge between past and future. Additionally, certain interpretations of quantum mechanics, such as the transactional interpretation, suggest that quantum events involve waves propagating both forward and backward in time, subtly hinting at the possibility of influencing the past. Yet, as with all grand ideas, time travel is fraught with paradoxes. The grandfather paradox, a scenario where one travels back in time and prevents their own ancestor from existing, illustrates the logical contradictions inherent in unrestricted time travel. If an action in the past alters the conditions necessary for the time traveler's own existence, how could they have traveled back in time in the first place? Some theories, such as the many worlds interpretation, offer a way out, suggesting that altering the past merely creates a new branching timeline rather than modifying the original. If true, this would mean that time travelers do not actually change history, but rather step into an alternate version of it. If even a limited form of retrocausality were achievable, our perception of history would no longer be fixed. Could we send quantum signals into the past to warn against catastrophe? Could a future civilization transmit knowledge back in time, altering the course of human progress? These are not merely academic musings, but questions that push the very boundaries of physics, touching upon the deepest mysteries of determinism, free will, and the structure of reality itself. The pursuit of quantum time travel is more than an exploration of physics. It is a challenge to the very fabric of our understanding. Whether time is an immutable river or a malleable construct remains to be seen. But one thing is certain: if quantum mechanics holds the key to time travel, then the universe is far stranger than we ever imagined. Time, the invisible thread that weaves the fabric of our existence, is often perceived as an unceasing flow, an unstoppable river carrying us from past to future. Yet, beneath this seemingly intuitive perception lies a profound mystery. Is time truly a continuous sequence, or is the present moment the only point of true existence, with the past and future as mere abstractions? While classical physics treats time as an immutable dimension, quantum mechanics suggests a far stranger reality, one where the past and future may not be rigidly fixed, but exist as probabilities, only materializing when observed. If this is true, then what does it mean to exist in the present? Could it be that the present moment is not simply where we experience life, but where reality itself is actively shaped? Throughout history, philosophers and scientists alike have grappled with the nature of time. In classical physics, Newtonian mechanics describe time as an absolute backdrop against which events unfold, independent of human perception. In this view, the past is a set of completed events, and the future is a predetermined path waiting to be realized. However, Einstein's theory of relativity disrupted this notion, showing that time is not absolute but relative, dependent on the observer's frame of reference. According to relativity, time dilates at extreme speeds and in strong gravitational fields, meaning that what one observer perceives as the present may not be the same for another. Yet, while relativity suggests that time is malleable, it still treats it as a continuous entity. Quantum mechanics, on the other hand, presents an even more radical picture, one in which time may not flow at all in the way we assume. Quantum superposition, the principle that particles exist in multiple states until measured, implies that reality is fundamentally probabilistic. If the future is not predetermined, but exists as a set of possibilities, then can we say that it truly exists before it is observed? Similarly, quantum retrocausality, a controversial yet mathematically consistent concept, suggests that present choices may influence past events at a microscopic level. If true, this would indicate that the past itself is not as fixed as we assume, but is also a set of probabilities that only collapse into certainty upon interaction with the present. If past and future exist only as probabilities, then the present moment becomes the point where reality is actively constructed. The famous double-slit experiment provides a striking example of this. When particles such as electrons are sent through two slits, they behave like waves, suggesting that they travel through both slits simultaneously. However, when a measurement is made to determine which slit the particle goes through, it suddenly behaves like a particle, and its wave-like properties disappear. In other words, the act of observation determines the outcome. This phenomenon suggests that the state of reality is not fully defined until it is measured, a principle that some physicists extend to time itself. If our observation is what collapses potential futures into a singular lived reality, then the idea of time as a pre-existing path may be an illusion. The past, too, may not exist in the way we typically assume, but instead emerges in relation to the present. The block universe theory, a concept in modern physics, posits that past, present, and future all exist simultaneously as a four-dimensional structure. But in the quantum realm, this view is challenged by the fact that past events may not be rigidly recorded, but could remain subject to later influences. living in the present, the intersection of science and philosophy. These ideas are not purely theoretical, they have profound implications for how we live our lives. If only the present moment is truly real, then the weight of past regrets and future anxieties begins to dissolve. In a quantum world where the past is not fixed and the future is still unwritten, we are granted an extraordinary freedom, the ability to shape reality not through deterministic chains of cause and effect, but through the choices we make now. Throughout history, Eastern philosophical traditions have emphasized the importance of present moment awareness. Buddhism, Taoism, and mindfulness practices have long taught that clinging to the past or worrying about the future blinds us to the reality of the present. Remarkably, modern physics seems to echo these ancient insights. If quantum mechanics suggests that reality is constructed in the now, then perhaps the wisdom of living in the present is not just a matter of subjective well-being, but a reflection of the deepest truths about the nature of time itself. Yet, embracing the present is easier said than done. Our minds are naturally inclined to dwell on past events and anticipate the future. However, just as quantum experiments show that observation influences outcomes, perhaps our focus, where we direct our attention, shapes not only our psychological experience, but reality itself. If the past is not rigid and the future is a field of probabilities, then the present is not just where we live, it is where we create. The more we explore the paradoxes of time, the more it seems that the present moment is the only point of actual existence. While memory allows us to reconstruct the past, and imagination enables us to anticipate the future, both are mental constructs, representations, not realities. If quantum mechanics is correct, then the past exists only insofar as it remains entangled with the present, and the future is a vast, uncollapsed set of probabilities waiting for observation to give it form. This perspective shifts not only our understanding of time, but our entire way of being. Instead of seeing life as a linear journey from birth to death, dictated by an inexorable march of time, we can begin to see it as a series of unfolding presents, each moment rich with the potential to shape what comes next. This does not mean the past is meaningless or the future should be ignored, but rather that our primary focus should be on how we engage with the now, the singular point where existence and consciousness meet, where reality is not merely experienced, but created. The future of time, unraveling the mysteries. Time, an ever-present yet elusive force, has long perplexed scientists and philosophers alike. Is it a fundamental property of the universe, woven into the very fabric of reality, or is it merely an emergent phenomenon, a construct of human perception? As our understanding of physics deepens, so too does our recognition of time's mysteries. Quantum mechanics, with its counterintuitive principles of superposition, entanglement, and non-locality, suggests that time may not be the rigid linear entity we once believed it to be. Instead, it may be malleable, dynamic, and even subject to influence in ways that defy classical logic. The quest to unravel time's secrets is far from over. In the coming decades, advancements in quantum theory, relativistic physics, and cosmology may redefine our most fundamental assumptions about the nature of past, present, and future. Could time be an emergent property arising from deeper quantum structures? Could it be possible to manipulate time, not merely as an abstract mathematical concept, but as a tangible aspect of reality? As we stand on the precipice of scientific breakthroughs, we find ourselves grappling not only with equations and experimental results, but with the profound philosophical implications of what it means to exist within time. Since the days of Newton, time has been treated as an absolute entity, an unchanging background against which the universe unfolds. This view was profoundly challenged by Einstein's theory of relativity, which demonstrated that time is not universal but relative, stretching and contracting depending on gravity and velocity. Time, in this view, is intertwined with space, forming a four-dimensional continuum known as spacetime. Yet, relativity, despite its elegance, still treats time as a dimension, much like space. It does not fully explain why time appears to flow, or why we perceive a distinct separation between past and future. Here, quantum mechanics introduces an entirely new set of questions. Unlike classical systems, which evolve in a predictable manner, quantum systems exist in superpositions where multiple states coexist until measured. This raises an unsettling question. If the future exists as a probability distribution, does it already exist in some sense, waiting to be collapsed into a definite reality by observation? Similarly, if quantum retrocausality is real, the idea that present choices can influence past events, then what does that say about the very structure of time itself? Physicists are now exploring these questions with increasing precision. Cutting-edge experiments in quantum computing, entanglement, and wave function collapse may soon provide empirical evidence to support or refute these radical interpretations of time. If time is indeed a product of deeper quantum phenomena, then future discoveries may lead us toward an entirely new framework, one where time is not an immutable feature of the universe, but a fluid, emergent quality shaped by quantum interactions at the smallest scales. With the rapid evolution of quantum mechanics and theoretical physics, several key discoveries could revolutionize our understanding of time in the near future. One of the greatest unsolved challenges in physics is the unification of general relativity with quantum mechanics. Many physicists believe that a successful theory of quantum gravity, such as loop quantum gravity or string theory, will reveal new insights into the nature of time. Some proposals suggest that time itself may be an emergent property arising from quantum entanglement rather than being a fundamental feature of reality. Recent discoveries in quantum physics have introduced the concept of time crystals, states of matter that exhibit periodic motion without energy loss. These bizarre systems challenge traditional notions of thermodynamics and could provide deeper insights into the nature of time symmetry. If time crystals exist in nature beyond controlled laboratory conditions, they could offer empirical evidence that time, like space, possesses hidden structures yet to be uncovered. While time travel remains speculative, some physicists are designing experiments to test retrocausality, the idea that future measurements can influence past quantum states. Certain interpretations of quantum mechanics, such as the transactional interpretation, suggest that particles may send signals both forward and backward in time. If confirmed, this could radically alter our understanding of cause and effect, potentially paving the way for novel technologies that manipulate temporal sequences at a quantum level. The scientific pursuit of time's nature is not merely an academic exercise. It carries profound philosophical implications, particularly in the realm of consciousness and free will. If the future exists as a quantum probability wave, does that mean our choices are predetermined, or do we actively shape reality with each decision? If retrocausality is real, could our present thoughts and actions ripple backward through time, subtly influencing past events? Perhaps most intriguingly, time travel, long relegated to the domain of science fiction, becomes a serious topic of philosophical and physical inquiry. Classical paradoxes, such as the grandfather paradox, have been challenged by new models of quantum mechanics. Some theories suggest that rather than altering the past, time travelers would enter branching timelines, meaning that each change results in a parallel universe rather than a modification of the original. This aligns with the many worlds interpretation, which proposes that every quantum event spawns multiple realities. The implications of time travel extend beyond mere physics. If it were possible to traverse time, even in a limited sense, it would challenge the very fabric of human experience. Would knowledge of the future alter our perception of destiny? Would awareness of multiple timelines expand or diminish our sense of agency? If we could send information to the past, how would history itself be rewritten, not just in books, but in our collective memory? As we look ahead, the pursuit of time's secrets is one of the most profound scientific endeavors of our age. Whether through quantum computing, new interpretations of relativity, or breakthroughs in consciousness studies, the nature of time may soon be understood in ways previously unimaginable. It is possible that in the near future, we will no longer see time as a simple progression of events, but as a dynamic, interactive field, one that we are not merely subject to, but active participants in shaping. While time remains one of the greatest mysteries of the universe, its future is clear. It is a frontier waiting to be explored. And as we stand on the cusp of discovery, we may find that time itself is far stranger, more fluid, and more mysterious than we ever dared to dream.
Time. It marches forward, unwavering and absolute, or so we thought. For centuries, humans perceived time as a rigid framework, ticking away at the same rate for everyone, everywhere. But what if I told you that time is not the steadfast constant we believed it to be? What if time, like a river, could speed up, slow down, or even bend? This is the mind-bending reality revealed by Albert Einstein's theory of relativity. Prepare to have your perception of time forever altered. Albert Einstein, a name synonymous with genius, revolutionized our understanding of the cosmos. His theory of relativity, presented in the early 20th century, shattered the illusion of time as an absolute entity. Einstein boldly declared that time is not absolute, but relative. Time, according to Einstein, is intertwined with space, forming a unified fabric called space-time. This fabric is not rigid but flexible, capable of being warped and stretched by gravity and motion. One of the most intriguing consequences of Einstein's theory is time dilation. Simply put, time dilation means that time passes at different rates for observers who are moving relative to each other. The faster you move, the slower time passes for you relative to someone who is stationary. Imagine two identical clocks, one remaining on Earth and the other traveling at incredibly high speeds. When the traveling clock returns, it will show a slightly earlier time than the clock that remained on Earth. This is not a mechanical error, but a fundamental principle of the universe. The faster clock experienced time dilation, causing time to slow down relative to the stationary clock. Let's dive deeper into time dilation with a thought experiment. Imagine a train traveling at near the speed of light. Inside the train, a passenger shines a light upwards to the ceiling. From the passenger's perspective, the light travels in a straight line, bouncing directly back down. However, to an observer standing on the platform outside the train, the light beam appears to travel diagonally. This is because the train is moving horizontally while the light is traveling vertically. Since the speed of light is constant and the observer sees the light travel a longer distance, time itself must slow down on the train for the observer on the platform. Time dilation is not just a theoretical concept, it has real-world implications. One of the most striking examples is the Global Positioning System, or GPS. GPS satellites orbiting Earth rely on incredibly precise atomic clocks to provide accurate location data.
However, these satellites are also moving at high speeds, experiencing a slight time dilation effect.
To compensate for this, GPS satellites have their clocks adjusted slightly, taking into account the time dilation predicted by Einstein's theory.
Without this crucial adjustment, GPS navigation systems would be significantly inaccurate, highlighting the tangible impact of time dilation on our everyday lives.
Section 6. Time dilation and astronauts. A journey into the future. In this chapter, we delve into the fascinating concept of time dilation and its profound implications for astronauts venturing into the vast expanse of space. The effects of time dilation become even more pronounced in the realm of space travel. As spacecraft travel at incredible speeds, approaching the speed of light, time itself begins to behave differently.
Astronauts aboard the International Space Station, orbiting Earth at high speeds, experience a minuscule but measurable amount of time dilation. This phenomenon, though subtle, is a testament to the intricate relationship between velocity and time. Orbiting Earth at high speeds, these astronauts are part of a living experiment in the effects of time dilation. The faster they travel, the slower time moves for them compared to those on Earth. Experience a minuscule but measurable amount of time dilation. Upon returning to Earth, astronauts are technically a fraction of a second younger than they would have been had they remained on the planet. This tiny difference, though imperceptible in daily life, is a glimpse into the potential future of space travel. Astronauts are technically a fraction of a second younger than they would have been had they remained on the planet. This phenomenon, while small, opens the door to intriguing possibilities for long-duration space missions.
While the time difference experienced by astronauts on the ISS is small, future missions to distant stars and galaxies could result in significant time discrepancies. Imagine a journey to a distant star system where the effects of time dilation become much more pronounced. Future missions to distant stars and galaxies could result in significant time discrepancies. For astronauts traveling at near light speeds, time would slow down dramatically relative to those on Earth. This means that while only a few years might pass for the astronauts, decades or even centuries could elapse on Earth. For astronauts traveling at near light speeds, time would slow down dramatically relative to those on Earth. This phenomenon, known as time dilation, could have profound implications for the future of space exploration and our understanding of the universe. Time would slow down dramatically relative to those on Earth. This means that while only a few years might pass for the astronauts, decades or even centuries could elapse on Earth. The implications of this are staggering, as it challenges our very perception of time and reality. They could return to Earth after years of interstellar travel to find that decades or even centuries had passed. This concept, while theoretical, is grounded in the principles of Einstein's theory of relativity and has been observed in various experiments, to find that decades or even centuries had passed. The future of space travel holds many unknowns, but one thing is certain: the journey into the cosmos will forever alter our understanding of time, space, and our place in the universe. Section 7. Extreme time dilation, black holes. The ultimate cosmic time warpers are black holes. These enigmatic objects are formed when massive stars collapse under their own gravity, creating a point in space with an incredibly strong gravitational pull. These gravitational behemoths possess such immense gravity that they warp the fabric of space-time to an extreme degree. The closer you get to a black hole, the more intense this warping becomes, leading to some truly mind-bending phenomena.
Time near the event horizon, the point of no return for a black hole, slows down to a crawl relative to observers at a safe distance. This boundary marks the limit beyond which nothing, not even light, can escape the black hole's grasp. If you were to observe a spacecraft falling into a black hole, you would witness a bizarre spectacle. The spacecraft would seem to slow down as it approached the event horizon, appearing almost frozen in time. As the spacecraft approached the event horizon, it would appear to slow down, its movements becoming increasingly sluggish. This is due to the extreme time dilation caused by the black hole's immense gravitational field, its image red-shifting as time itself stretched to infinity. The light from the spacecraft would be stretched to longer wavelengths, making it appear redder and dimmer to an outside observer.
From the spacecraft's perspective, however, time would seem to flow normally, as if nothing unusual were happening. The crew inside would experience time at its usual pace, unaware of the dramatic time dilation occurring outside, a testament to the relative nature of time. This phenomenon highlights the fascinating and often counterintuitive effects of extreme gravity on the passage of time, reminding us of the complex and mysterious nature of our universe. Section 8. Time travel. A distant possibility. The concept of time dilation inevitably leads us to ponder the tantalizing possibility of time travel. Could we one day harness the power of time dilation to journey into the future or even the past?
While time travel remains firmly in the realm of science fiction, Einstein's theory does not explicitly rule it out. Some physicists speculate that wormholes, theoretical tunnels through space-time, could potentially act as shortcuts for time travel.
However, the existence of wormholes remains purely theoretical, and even if they do exist, navigating their unpredictable nature would be an immense challenge.
Section 9. Conclusion. Time is a river, not a straight line. Einstein's theory of relativity shattered our Newtonian view of time as an unwavering constant. Before Einstein, time was seen as a universal clock, ticking away uniformly for everyone, everywhere. This classical view was comforting in its simplicity, but it was also misleading. Einstein introduced the radical idea that time is not absolute. Instead, it is intertwined with the fabric of space itself, forming what we now call space-time. We now know that time is a fluid and relative concept, influenced by gravity and motion. Imagine time as a river, its flow changing speed and direction depending on the landscape it traverses. In the presence of massive objects like planets and stars, the river of time bends and slows. This phenomenon, known as time dilation, means that time can pass at different rates depending on where you are and how fast you're moving. Time dilation, a consequence of this revolutionary theory, has profound implications for our understanding of the cosmos and our place within it. For instance, astronauts aboard the International Space Station experience time slightly slower than we do on Earth. This effect, though minuscule, is measurable and has been confirmed through numerous experiments. It challenges our intuitive understanding of time and forces us to rethink our place in the universe. From GPS satellites to the journeys of astronauts, time dilation is not just a theoretical curiosity, it is a fundamental aspect of our universe. GPS systems, which we rely on daily for navigation, must account for time dilation to provide accurate positioning. Without these corrections, the system would quickly become unreliable. This real-world application underscores the importance of understanding time as a dynamic and relative entity. As we continue to explore the cosmos and unravel its mysteries, our understanding of time will undoubtedly continue to evolve, leading to even more mind-bending discoveries. Each new mission, each new observation, adds another piece to the puzzle. The more we learn, the more we realize how much we have yet to understand. The journey of discovery is ongoing, and the river of time flows ever onward, carrying us toward new horizons. Ultimately, time is not a straight line but a winding river, its flow forever intertwined with the fabric of space-time. Just as a river can carve through mountains and shape the land, the flow of time shapes our universe and our understanding of it. Embracing this fluid and dynamic nature of time opens up endless possibilities for exploration and discovery, reminding us that the journey is just as important as the destination. The concept of time travel has captivated the human imagination for centuries. From ancient myths to modern science fiction, the idea of moving through time has always fascinated us. We see it in literature, film, and our wildest dreams. The notion of stepping into a time machine and visiting different eras is a recurring theme that never loses its charm. The ability to journey through time, to witness historical events, or to get a glimpse of the future holds an irresistible allure. Imagine standing on the deck of the Titanic or witnessing the first moon landing. This desire to explore the unknown, to change the past, or to peek into the future is a testament to our innate curiosity about the nature of time itself. It's a reflection of our deepest desires to understand our origins and destiny. But is time travel merely a product of our imagination, or could it one day be within the realm of possibility? Could we ever build a machine that transcends the boundaries of time? Science fiction has explored the possibilities and consequences of time travel extensively. These stories stretch our minds and challenge our understanding of reality. From H.G. Wells' The Time Machine to the intricacies of the Back to the Future trilogy, we have been both entertained and challenged by the implications of manipulating time. These narratives invite us to ponder the ethical and moral dilemmas of altering history. These stories often serve as cautionary tales, highlighting the potential paradoxes and unintended consequences that could arise from tampering with the fabric of time. They remind us that with great power comes great responsibility. While time travel remains a theoretical concept, the pursuit of understanding its possibilities pushes the boundaries of our scientific knowledge. Researchers continue to explore the mysteries of time and space, driven by the hope of one day unlocking its secrets. It compels us to ask fundamental questions about the nature of the universe, the nature of causality, and our place within the grand tapestry of time. The allure of time travel is not just about the destination, but the journey of discovery itself. Albert Einstein, the renowned physicist, revolutionized our understanding of space and time with his groundbreaking theory of relativity. His insights have fundamentally changed the way we perceive the universe and our place within it. His work laid the foundation for the theoretical possibility of time travel, suggesting that time is not absolute but is relative to the observer's frame of reference. This was a radical departure from the Newtonian view of time as a constant, unchanging entity. Einstein's equations showed that time can be stretched and compressed, a phenomenon known as time dilation. This means that time can flow at different rates depending on the speed at which an object is moving. One of the most intriguing aspects of relativity is the concept of time dilation. which states that time passes slower for objects moving at high speeds relative to a stationary observer. This has profound implications for our understanding of time and space. This effect becomes more pronounced as an object approaches the speed of light. The closer an object gets to this ultimate speed limit, the more time slows down for it. For example, if one were to travel in a spaceship at a significant fraction of the speed of light, time would pass slower for them relative to someone on Earth. This is not just a theoretical concept, but a real effect predicted by Einstein's equations. This means that upon returning from their journey, the traveler would have aged less than their Earth-bound counterparts, essentially traveling into the future. This fascinating idea has captured the imagination of scientists and science fiction writers alike. While achieving such speeds is currently beyond our technological capabilities, the concept of time dilation has been experimentally verified using atomic clocks. These experiments have shown that time does indeed pass at different rates depending on the relative speeds of the clocks. Another intriguing concept that emerges from Einstein's equations is the possibility of wormholes, theoretical tunnels that connect two distant points in space-time. Imagine folding a piece of paper in half and poking a hole through it. That's a simplified visualization of a wormhole. These cosmic shortcuts could potentially allow for travel across vast distances, even between different points in time. However, the existence of wormholes remains purely theoretical. One of the major challenges lies in the fact that they are incredibly unstable and would require exotic matter with negative mass energy density to hold them open. This type of matter, while theoretically possible, has never been observed. Despite these challenges, the concept of wormholes continues to fascinate physicists and science fiction enthusiasts alike. If we could somehow harness the power of wormholes, we might be able to unlock the secrets of time travel and explore the universe in ways we never thought possible. Beyond wormholes, another theoretical construct proposed by physicists is the cosmic string. These are hypothetical, one-dimensional defects in space-time, remnants of the early universe's formation. Imagine them as incredibly thin, extremely dense threads of energy stretching across the cosmos. While their existence is yet to be confirmed, some theories suggest that cosmic strings could potentially be manipulated to create closed, time-like curves, essentially loops in space-time that could facilitate time travel. The immense gravitational pull of these cosmic strings could, in theory, be harnessed to warp space-time sufficiently to create closed, time-like curves. A spacecraft, for instance, could theoretically travel along such a curve, effectively traveling back in time. However, the challenges associated with manipulating cosmic strings are even more daunting than those posed by wormholes. Not only do we need to confirm their existence, but we also need to develop a deep understanding of their properties and the technology to harness their immense energy. While the concepts of wormholes, cosmic strings, and time dilation offer tantalizing possibilities for time travel is riddled with paradoxes that challenge our understanding of causality and the very fabric of reality itself. The most famous of these is the grandfather paradox, a thought experiment that has puzzled scientists and philosophers alike. It poses a rather disturbing question. What would happen if you traveled back in time and accidentally killed your grandfather before your parent was born? Would you cease to exist, vanishing from the timeline as if you were never born? Or would the universe unravel, unable to reconcile the paradox, leading to a cosmic disturbance? This thought experiment highlights the potential contradictions inherent in time travel, making it a fascinating yet perplexing topic. Several solutions have been proposed to address the grandfather paradox, each with its own intriguing implications. One possibility is the existence of parallel universes or alternate timelines, where each action creates a new branch of reality. Perhaps traveling back in time transports you to a parallel universe where you can interact with the past without altering your original timeline, thus avoiding any paradox. Another solution is the Novikov self-consistency principle, a theory that offers a different approach to resolving these paradoxes. This principle posits that if you were to travel back in time, something would always prevent you from changing the past in a way that would create a paradox, ensuring that events remain consistent. Essentially, the universe has a way of self-correcting to maintain consistency, preserving the balance and order of the cosmos. Even if we could overcome the paradoxes associated with time travel, the practical challenges are immense. Creating wormholes or manipulating cosmic strings would require unimaginable amounts of energy, far beyond our current capabilities. We would need to develop technologies that can harness and control these energies, a feat that currently lies firmly in the realm of science fiction. Furthermore, the stability of wormholes or time-like curves created by cosmic strings is questionable. Maintaining a stable passage through time would likely require a mastery of exotic matter and its properties. We are still a long way from fully understanding these theoretical concepts, let alone manipulating them to our advantage. While time travel remains a distant dream, the pursuit of understanding its possibilities continues to drive scientific inquiry and technological advancement. While we may not be hopping into time machines just yet, we do have concrete evidence of time dilation, one of the intriguing consequences of Einstein's relativity. Experiments with atomic clocks have demonstrated that time does indeed pass slower at higher speeds. For example, atomic clocks flown on jets have shown a minuscule but measurable time difference compared to their Earth-bound counterparts. While this time difference is incredibly small, it provides tangible proof that time is not absolute, but is influenced by speed. This subtle manipulation of time, while not quite time travel in the traditional sense, offers a glimpse into the mind-bending possibilities that govern our universe. Time, as a concept, continues to fascinate and baffle physicists and philosophers alike. Is it a fundamental aspect of the universe, or is it an emergent property arising from something more fundamental? Does time flow in one direction, or is our perception of its passage merely an illusion? These questions lie at the heart of our quest to understand the nature of reality. The pursuit of time travel, whether it remains a distant dream or becomes a future reality, compels us to confront these fundamental questions and to expand the boundaries of our knowledge. While the practicalities of time travel remain firmly in the realm of science fiction, the pursuit of understanding its possibilities continues to inspire scientific exploration and technological innovation. The quest to unravel the mysteries of time pushes us to ask fundamental questions about the universe and our place within it. Who knows what breakthroughs await us in the future? Perhaps one day, armed with a deeper understanding of the cosmos, we will unlock the secrets of time travel and embark on journeys through the annals of history or into the uncharted territories of the future. Until then, the dream of time travel will continue to fuel our imaginations and inspire us to push the boundaries of human ingenuity.